more daunting than they actually are. The only thing that's kind of stuck is like, what is Q? Why is Q? Who is Q? Q is me. This one or I probably would have got this wrong. But now that I've seen it, it's like a 50-50 chance. Now that I've seen it,
jeez.
it's like a 50-50.
At least the volume's working.
Volume works, yeah. Inside the computer?
No, is it on like the back side of the computer, like right in front of us? Or just
No, like I have a mic right here, and just it's facing me, but could be better. All right, cool. So we've got 2 more questions for the homework. We'll see if we can get through. Chapter 3.
You still have pre-class quizzes to do?
I'm just pulling up
For this class.
this problem. Yeah, down here.
Okay, I remember for statics it was like 3 class quizzes you have to do.
Oh, look, you know statics is not even, I feel like it's just
Well, no, I mean, you. Yeah. Okay.
my notebook is like
Wow.
All right, so we've got, I'm gonna redraw the balloon because it's important. It's gotta be red balloon, right? So let's get that out of the way. Cool. All right, so we have this red balloon, and we have a string tying it down to the ground. And first step, it's telling us like just consider it as a point mass. But why consider like a balloon as a point mass? Like why not think about its rotational inertia? Yeah.
what question number is this?
This is 334. Is that right? 34. Which is, yeah, it's like second to last in our like homework as we're working through. Yeah, thanks. I was trying to jump in, rush right into it. But yeah, what kind of questions would you answer that's like a point mass for the balloon rather than like considering it as a rigid body? Like what do you lose or what do you gain? Like, yeah.
Point mass kind of helps you ignore the mass of the string.
Ignore mass of string, maybe. Yeah, it might help.
Well, I think
Yeah.
point mass like averages the forces over the entire balloon. So like a point mass, it's kind of hard to show that a point mass is rotating, whereas a rigid body, you can apply like a torque and see exactly where it's being applied to on the balloon.
Okay. Yeah. So so when we say that it's a point mass, it doesn't matter if there's torque on it because there's no. Even if it is rotating, we're not considering rotation. Like it's just a point. So whether it's upside down or right side up, it's still just a point. And the main thing is like all the forces are going right through the center of mass. So we're not considering like that. Like the balloon can't do this, right? Like, because if you've held a balloon before and like yanked on the string, the balloon rotates and then follows, but we're not considering that. we're just gonna say point mass. That's okay. So what does the free body diagram look like? I think there's a little information. So you try drawing free body diagram. I'm gonna grab the extra info here. And then we also want kinetic diagram. Yeah, so there's also like buoyancy is double the weight. Like it's twice as buoyant as it is heavy.
No, but I think we can kind of figure it out. I don't know if we'll need to. That's my one thing to do. Yeah. I think like buoyancy is just 2m, and we just use that for our equations. We might not get equation.
That could be part of it. So when we get an equation,
So
yeah.
How do you do like the buoyancy?
In this case,
So you just have
if we assume that it's a point mass, then it's just like a lump of thing. And it goes straight at one angle, then it's going to like swing to the side.
Also, I think
Yeah, yeah. Yeah, that's kind of like what we're losing by. Yeah, so if it's over there, then there's no force holding it there, so it's going to swing the other way. At least that's what I think. Yeah. Yep. Helium. Yeah, helium is going to increase buoyancy. Air.
Oh, I saw those type of records.
Is there? Yes. Is there like
Probably like helium since force buoyancy is double.
Ich will da hier straight up. Steve, what is that? Steve, we need to get out of it now. So I think what you take right is no higher than it is.
Alright, cool. Forces are not balanced, right? At least the way that we're kind of drawing stuff right now. So weight.
There is some sort of motion.
It's just going to want to swing to the right until it's vertical.
And then like buoyancy. And then, yeah.
Mike brought up the point, since it's 2 times the weight, force of buoyancy is 2 mg.
Yep. Yeah, so we could, like we could take both of those and add them up directly, right? And then we just have one mg pointing straight up. And then I saw something like pointing along that string, like along here. Saw it labeled like tension or something where like the cord will not stretch. It's just, and it's not going to, as long as tension is positive, it's just a tight like rope holding that balloon down. All right. And that was, yeah, sketched point mass. What kind of, oh wait, draw a free body. I guess we also drew that free body, right? And that's fine. What kind of coordinate system do you think would work for this? Maybe polar? Or inertial, yeah. So when we're drawing,
Relative to the fixed point, so maybe some sort of system.
yeah, like we could say that this is theta, and then there's got to be some like L, like the balloon is always at least center of mass. It's like L away from that point. We can also use that inertial frame, like when things are moving in a circle, and it works out kind of both ways. So what does our kinetic diagram look like? And that's what this is when it's asking, like, what are the inertial kinematics? Really, it's like that kinetic diagram. What is that? What is our kinetic diagram for this part? Yeah.
I guess it's inflation is maybe you don't want to rotate. It's probably like I guess realistically oscillate until like the balloon is directly vertical.
Ooh.
With the relative to the base of the string.
So you think it's gonna come to a stop?
I'm not sure if it'll come to a stop.
Yeah.
I guess realistically, yes, but in this one, there's no air resistance, so I actually don't know if there's anything stopping. There's nothing stopping, so no.
Yeah. What do we think? Yeah.
So like an MA tangential to a circular path that's going to take.
Oh, okay. Yeah, you want to put like along that tension, we'll say is MA. What kind of MA?
Yeah, I said it was perpendicular, like tangentials.
Oh, 90 degrees to that?
Yeah.
All right. I'm going to draw it this way. There's like two components, right? So we can always break things up into whatever components we want, as long as it's 90 degrees from each other. And if we're gonna say that it's 90 degrees off of where the balloon is, that angle is gonna change. So now we're using some kind of rotating coordinate system, like polar. Polar is one of those. Inertial is another one. So what are these two components? What are they? At least the labels, like X and Y, 1 and 2, A and B. I don't know what kind of labels would we put for those? X and Y. So you want to have like a. We could do. You can do X prime, Y prime. Like X prime, Y prime, something moving. What does that look like for polar coordinates? Like which one? What is X prime if you're talking about like a polar coordinate system? R and theta. Yeah, I heard like whispers. R and theta. One's R, one's theta. Which one's R?
X prime.
X prime, yeah. So like another way, we could say that this is like my ER direction, my E theta direction. And the only reason I do that is that we have definitions for acceleration in that polar coordinate system. We can just plug in those definitions of like what is acceleration in this rotating reference frame. How do I know R versus theta?
Yeah.
R is always going to describe like a radius. it's always describing how far away from an origin we are, and then theta is describing the direction. So r is magnitude of position, and then theta is describing like where, like what angle it's at. Yeah, and here I specifically, I'm maintaining like theta right-hand rule positive. That's what I like to do in general. You don't have, like, you could say E theta is pointing the opposite way, but you just have to make sure that you're properly maintaining your unit vectors. Wow, it's just bookkeeping is the main thing. So we have, once we say like, hey, we're using polar coordinates, it's always the same definition. We can always look it up. I've looked it up enough times that I can just write it down, and you can look it up right there. Now we can make it gets simpler because some stuff is 0 in this equation. Let's take a second, try crossing out what's 0 in our acceleration terms.
Well, R's not changing. R is constant. So yeah, R dot and R double dot are both in.
Oh, I can say it. I think we all know the number, of course. Well, I can't do that. I say something that's very common. Says the exact same thing.
You just tell me. It's good.
So,
Got one term for each one, right? R theta dot squared and R theta double dot. Which one's going to define our equation of motion? Or sorry, equations. We could have equations of motion. I jumped a step. How many equations of motion do we have? 2? 1. 2 or 1? A negative 1?
no.
Oh.
How do we only have one?
Or 1? That's a good question. Yeah. How do we know how many equations of motion we're supposed to have? Degrees of freedom, right? 1 degree of freedom are, so we have like a constraint, right? We assumed it was a point mass, so a point mass only has 2 degrees of freedom, but we're saying R is constant, 1 constraint. So we're only gonna have one equation of motion. We have a vector system, so it's still going to give us 2 equations, but only one of them is describing like the actual independent equation of motion. Or sometimes you have to like add them together, but like somehow, at the end of the day, 1 degree of freedom, 1 differential equation. All right, what forces are radial and which ones are transverse, like theta and r? Which one's a theta force, which one's an r force?
I think the tangent, not the tangent,
The T, that,
T,
yeah,
yes.
that big T. What do you think?
tension force.
Tension?
That's-
Yeah.
That's the one within the radial direction.
Radial? Okay, so we'll throw that one in here. I'm going to put a negative since I said going out is positive. And it's good to like maintain that of like, if you say R positive is moving away from the origin. Every force pushing you towards the origin is negative. So just try to like keep a consistent system. Otherwise you end up with like positive negatives, like flip-flopping all over. All right, so tension, we got that one covered. Buoyancy, gravity, where are those pointing? There's some angle, right? So now we got to do some trig or some geometry, I don't know, parallel lines. Do you want to add the two forces so we only have to deal with one?
Yeah, because you have negative mg plus 2 mg. So you said
All right. Nice, like quick high school geometry problem. Label the congruent angles in this parallel system. So now we have like two components, right? We're splitting mg into some kind of radial component, some kind of theta transverse component. It's got to be sine and cosine. Is it? Which one's radial, sine or cosine? Cosine? Yeah, yeah. Yeah, it's right next to it, right? So then this one's got to be sine. Are they positive or negative?
basically like the mg cosine.
Positive mg cosine? Yep. And then what about theta? Is the force creating a bigger angle or is the force creating a smaller angle? Is it pushing it to 0 or is it increasing it bigger? Pushing it back to 0, at least in this case. If it's negative, then it's going to push it back to 0 again, but. Yeah. Well, vacuum, then there'd be no buoyancy, though. Yeah. Yeah, you need the air to create. So we can say that it's in a vacuum, but then it's just a balloon sitting on the floor with like a string sort of curled up below.
Wait, so the helium wouldn't be, because I guess the reason the balloon floats is because it's less dense than the air around it, but there's no air around it.
Yeah. Yeah, like you need.
Oh, but it's not less dense.
You need to displace volume to create buoyancy. So if there's no volume to begin with, well, one, the balloon would explode because now you have 1.01 atmospheres inside of a 0 atmosphere. So now you just created a huge vacuum to like yank the balloon apart. So I guess not only would it be sitting on the floor of the vacuum, but it would also be in pieces on the floor of the vacuum. But we can assume it's a vacuum. It's not as fun. I mean, I guess the explosion part would be fun, but less math, I guess, which is nice. All right, so we know which forces are acting which direction. I think we got all the plus minuses, and we accounted for all of the forces here. What is our equation of motion? What does it look like?
That's what I'm thinking.
Yep. Okay. Oh, trying to solve. And R is going to be like something constant, right? Like, one, two, three. Yeah. Yeah.
With the AR and data.
Yeah. Yeah. I mean, that's what I'm saying. Take my definition.
Wait, so what?
To those equations that you just made.
About the bug?
Yes, the MAR.
It's not
and
that
the
way.
MAP.
It's a
You can appreciate it to MAR plus anything squared.
Yeah. Oh, yeah, yeah.
Because that is MA subscript R, MA subscript theta. So those are forces. You just have to-
But it's moving against
R and MA data.
Yeah. Yeah. there's no-
constant speed around the curve.
They know we're-
Still have separation.
What?
ETM.
Environmental.
Oh, no. I remember seeing that. Because that's how it's negative twice.
Environmental. Protection.
Yeah.
I have no idea.
I know it's like
What did we do in the last round?
Yeah.
he didn't use this. He didn't know how to do it.
They're in their
There's nothing like that.
Do like the.
out like some kind of problem.
Yeah.
You're moving around the curve.
It's recommended you take it this summer after you
Then you
graduate.
constant.
Because the longer you take it, the longer you wait.
And then they did that. I didn't do school.
So it's recommended you stay as fast as possible. Well, not as fast as possible, but as fast as possible.
Yeah.
It's probably a good idea to keep saying the notes then. It's not necessary, it's just better to have it. Because if you have to give it more classes, they won't prevent you from doing a job.
Yeah.
It's like if you want, it's like if you want to create your own figure out there.
We used to think of wind as like their
Yeah. If you don't do the work as an engineer, you
it'll
don't
change
change
like
as
First data goes to
the equilibrium position of what the wind is.
So it's gonna be
Well, so like,
I don't think three of us. And more people go through this than that exam. Maybe.
Yeah. So that's why
On the exam?
But you have like,
Including physics.
you have equations that are taken.
whether it's rotating.
Because I hate physics, I still think it's better. Sorry, how much time? It's 38. You don't need like that.
And for the most part, like.
So the leave is the problem if you wanna leave.
It'll
be 45 minutes.
The balloon's up to, I don't know, 2 ounces.
Yeah.
Oh, yeah. Says no droppings. Oh, that's great. No droppings today.
Yeah. Okay. Oh, you're like trying together. Okay. Okay. Which one is your like equation motion? Not sure. Yeah.
So wait, we get out of
Yeah.
So like
Yeah, like if you have initial position and velocity.
yeah, you do the initial paradigm,
Yeah.
constant acceleration.
Oh, assume constant.
I don't know, we
Oh,
could
okay.
maybe
Yeah.
a small angle to move.
Yeah, yeah. We can assume small angle.
I know where to go from there.
Yeah, yeah. Okay. All right, so we're gonna delete the magic arrow, start plugging in values, right? Negative mr theta dot squared equals negative t. That's like one equation. My second equation is mr theta double dot equals negative mg sine theta. And I think for the most part, people were kind of coming up to this spot. So we can start getting rid of m's, right? Like make this a t per m. We can make that. We can get rid of that r and say that it's g over r. Yeah, something like this. But, and this is okay, like if this is where you got to and you're kind of like, all right, what do I do from here? So when I look at this, the first thing that I think of is like, all right, I've identified one equation of motion and an equation to solve for what tension is. I can kind of walk you through that. So looking at equation 2, this is acceleration and angle. So it's a second order differential equation that says the angular acceleration is always equal to some function of the angle, which is basically a spring. Because like the bigger the angle, the more acceleration it's going to launch it back up, and then swing through, and then stop again, and then swing back up. We have that sine theta in there, but whatever. So it's a nonlinear spring. So that's, when I look at that, I say like, all right, this. Oh, why does the m? When I look at it, I say like, all right, this is my equation of motion because it's a second order differential equation describing acceleration and position. It's not exactly like r, but it's theta. And if I know theta, I know everything I need to know about the balloon. Then equation 1, really what this one's telling you is that if you integrate this, then you have theta, theta dot, and theta double dot. Like you have all three of those values. So you can plug in theta dot and solve for t. So t is now a function of theta dot and theta. Because we don't know what the tension is until we know how fast it's moving and where it is. Does that make sense? Because like if you take the balloon and bring it down to the ground, then for that instant there's no tension. If it's not moving and mg cosine is 0, then there's no tension in it, and then it starts swinging up. Now the tension increases. It's moving faster as it gets to the top. Now you have max tension, and then it swings back around. Oop. Or minus t. Positive, yeah, plus. So anyway, we're just asked for equation of motion, but if you're trying to figure out like what is that second equation, like why do I have these two equations? That's what it's there for, is that we said tension has to be there, and it has to make sure it travels in a circle, and we can calculate it because we have that equation now. Yeah?
To be clear, to solve the second equation, we can just integrate twice with respect to theta.
Yeah, for this one, we would have, like if we want like theta, like what is theta as a function of time, then the easy, so easy-ish is easy-ish way is say sine theta is theta. So that's true if the balloon is only going, my rule of thumb is about 30 degrees. If it's 30 plus minus 30, then we're fine. If it gets up to like 60 or 90 degrees, then now we're introducing like nonlinear things. So then theta double dot is negative g over r times theta. Now I know theta of t is, actually I'll plug it in. Initial theta cosine root g over r times t plus initial speed over root g over r times that sine root g over r times t. Oh, and you can't see most of that, huh? So if the next step is like, all right, what do I do with that information? Like I have an equation of motion, how do I integrate it? Usually the easiest way is like try to turn that general equation of motion into a linear one. Linear equations are easier to integrate. And then we know like whatever its initial angle is times cosine, and whatever its initial speed times that sine component. Yeah.
In this group, are those G's or theta?
Those are G's. Yeah, all G's.
And they're inside the cosine function too with t.
Yeah, like that. Like that. Sorry, it's catching up. Because that's our natural frequency is root g over r.
How did you get those equations? Like, I guess how did you get them?
They were delivered me from Jesus, from the Jesus, yeah. No, they're, this one, and I guess that's the next problem too. It's like create an equation of motion and then get to this equation, like get to this part. So you can derive them, like do a Taylor series expansion or polynomial series. But for the most part, if you know that double dot equals something times the original, so like x double dot equals usually like k over m times x, then the answer is always going to be like some kind of cosine plus some kind of sine. The frequency is, yeah. So if we have like a general, so if this is, I assume that this is the answer, so then x double dot is, and I know it's time for the exam. So if I assume that's the answer, then its second derivative, it looks like this, which is like negative omega squared times the original. So now negative omega squared x equals negative a x. So a is square root, or sorry, omega is square root a, like that. And then I can plug in, and usually a is like a g over L or a k over m, like some kind of like stiffness per mass number or something like that. And yeah, we're out of time, at least for today, so that you can get to exam. All right. Good luck.
Are we gonna do the last homework on next class?
And then I guess next class we'll do the next problem. It was supposed to be, we were supposed to finish today, but I guess we'll just finish Wednesday. That's all right. We'll get there. Thanks. Yeah.
Question.
Yeah.
Determine which way you had theta goes. What is it like the way the angle increases?
Yeah, so E theta is always going to describe an increasing theta.
So from like the top, that's why like from the top it's going to the, like down and to the left, because like that's the way the balloon should be going to increase the angle.
Yeah, so at least the way that I like to do it is say that right-hand rule is a positive theta, so then E theta is describing like when I increase theta, where does my balloon go, or where does my like point go?
Got it.
Yeah.
Thank you.
Cool, thank you. And then ER is always like, yeah, just pointed at the thing. That one's a little easier to figure out, but ER gets flipped around depending on if it's upside down or sideways. Or, yeah. All right, cool. Are you also doing exam? Okay, all right, enjoy the time. Enjoy the extra time then.